Hi guys, we're back with another video. It's kind of been a minute, but I saw a request for this, so today we're doing rotting oranges. So we're given an M by N grid where each cell can have one of three values: 0 representing an empty cell, 1 representing a fresh orange, or 2 representing a rotten orange. And they say every minute, any fresh orange that is forward directionally adjacent to a rotten orange becomes rotten. So they want us to return the minimum number of minutes that must elapse until no cell has a fresh orange. If this is impossible, return -1. So they give us this example here where we start with just the top left orange being rotten, as we can see, because there's a 2 in the grid. So let's copy and paste that so we can see what's going on here. Okay, so basically we have this, and so they tell us that 2 is a rotten orange. So we have 2 in this corner here, which is what we see here. The X is representing a rotten orange. And every single iteration or minute, the ones that are directly adjacent to the rotten orange become rotten as well. So here, these 2 become rotten. So our grid would start out like this in iteration 0, like this is initial. Then we'll just say minute 0. This is minute 1. Then these 2 that are directly to the right and down from it also become rotten. So the ones become 2s here. See that? And then the next minute, so in minute 2, then the ones that are all next to all the 2s become rotten. So this 2 is next to the 2, so it becomes rotten. This 1 is next to both of these, so it becomes rotten. Zeros, nothing happens because there's no orange there, right? The 0 represents an empty cell. So there's no orange there, so that doesn't change. And then we get this, which if we can see here, then this is the same thing, right? So then the next minute, all of the ones that are next to the 2s become a 2, so that becomes a 2. And these are zeros again, so that doesn't get affected. So that this matches up with this, right? Then in minute 3, we only have this one left, and that becomes a 2, and then we're done with our grid, right? So then we check the number of minutes that, wait a minute, 0, 1, 2, this is supposed to be a 3, and that's supposed to be a 4. There we go. So then because it took us 4 minutes to get to this stage where all of the oranges are rotten, we would return 4. So in example 2, we're given this grid, and they say the orange in the bottom left corner is never rotten because rotting only happens 4 directionally. So we can take a quick look at this one too. Okay, so here, this is going to be minute 0, that's our initial state, right? And then let's also label this example 2. So minute 1, then the ones that are next to the initial, like initially only this cell is a 2, right? So then this one would also become a 2 in minute 1. And then in minute 2, these 2 become 2s. And then in minute 3, this one becomes a 2. And then in minute 4, oh geez. This one becomes a 2. And then, as you can see, like, even if we extend to another minute 5, nothing else can possibly happen here because this orange is stuck in the corner with 2 gaps in between, so it can never possibly be reached by the rotten oranges. So, because we can't possibly get this one to be rotten, we would return -1, right? Because we want to return the number of minutes it takes to turn all the cells rotten, and that can't possibly happen in this case, so we would return -1. And then in example 3, we return 0 because I guess there's an empty orange and a rotten orange. I mean, an empty cell and a rotten orange. So because there's no fresh oranges that we can even turn rotten, then we can just immediately return 0 because there's no fresh oranges to become rotten, right? So this one, as you can see here, we're kind of going layer by layer through a graph, through a cell, which is representing a graph. So we basically want to do a BFS for this one, starting with all of the rotten oranges as our root for our BFS. Okay, so we can start with our base cases, which is that if we are given an empty grid or the grid is null, then we can just return 0 because there's nothing to even search. So if grid is null, or the length is 0, just return 0. And then we can initialize our queue for our BFS. And we're going to want in a variable to keep track of the number of fresh oranges that we have. And that is because, well, first of all, if we don't have any fresh oranges to begin with, then we'll just return 0 because there's no oranges to even rot in the first place. But we also need this because in the end, if, like, for example, if we go back down to, where was example 2? Yeah, so like in example 2, we were already done with all of the iterations. Oops, what happened here? That should be like that. Okay, so like in this case, right, like we were done with all of the iterations, and this one in this bottom left corner is left fresh. Like it couldn't possibly have rotted because both of the oranges next to it, both of the cells next to it are empty. So that's how we'll know that we need to return -1 and it's impossible to rot all the oranges, because we'll still have a fresh orange left over by the time we're done with our BFS, which we're keeping track of using this variable. So that's how we'll know. So the first step then is to add all of our rotten oranges onto our queue, and that's where we're going to start our BFS from. So we'll say for row is 0, row is less than grid.length, row plus plus, column, then if grid at row at column is equal to 2, so that means that if we have a 2 here, that means it's a rotten orange. So then we're going to want to add this onto our queue. So queue.add, and we're just going to push the coordinates of that cell onto our queue so that we can keep track of its location. So we'll say row and column. Else, so if it's a fresh orange, then we're going to want to increment this variable instead, because it'll be a fresh orange. So if grid at row at column is 1, then we'll increment fresh. And that's basically it for adding onto the queue. Then if we're done with all of this and there's no fresh oranges, then we know we have something like example 3, and we can just go ahead and return 0 immediately without even bothering with the BFS. So we can go ahead and say that. So if fresh is 0, return 0. All right, and then we want to set up our directions array so that we know which directions to look at when we're doing our BFS. So in this case, we can only go up, left, down, and right. We can't possibly go diagonally. So we'll just include that, and then that way we can iterate through each direction when we are looking at where to explore. So we'll say int, double int actually, directions equals, and then we'll just put all of the possible directions in here. So we'll say 1, 0, negative 1, 0, 0, 1, and 0, negative 1. And then we also want to keep track of the number of minutes that have passed. And we'll start it off at negative 1. Because we need to know the number of minutes that we need, like basically we need to count the number of minutes that elapsed during our BFS. So we're just gonna keep track of that. So now we can start our actual BFS. So while our queue is not empty, then we'll just do a regular BFS pretty much from all of the rotten oranges. So we'll just keep track of oranges in current level, spelled current wrong, equals queue.size, and we'll increment the minutes passed immediately. So then this will become a 0. Then now we can loop through. So this is like, yeah, this is like to keep the BFS going, and then now we're gonna loop through all of the nodes or cells with oranges that are in our current like level of our graph, which is what's currently in the queue. So for int I is 0, I is less than oranges in current level, I plus plus. Then we are going to want to keep track of the position of our current orange. So we'll remove it from the queue, and then we'll assign the row to position at 0 and the column to position at 1. Right, because when we extract a cell, like let's say our current cell is literally just that first one, right, 0, 0, then, or that's kind of a bad example because the row and column are the same. Let's say we're at minute 1 and it's 0, 1, right? Then the row is going to become 0 and the column is going to become 1. Okay. And so now we're going to loop through all of our directions. So like for this orange at this position, we're going to loop through each direction. So we're going to look left, up, down, and right. And then obviously like we can't possibly look up because there's no actual cell there. It's off the grid. So we're going to make sure to check for that. And then left, we already have a rotten orange, so it can't possibly rot. So basically we're just looking at right and down. But yeah, so we're going to need to loop through our directions to do that, and then just add an extra check to make sure we're not doing like invalid inputs or something. I don't know if that's the right word, but you know what I mean. So for int direction in directions, so then whatever our new cell is, like let's say it's this one, we're going to need to store the coordinates of that cell. So we're going to want to keep track of the row, which is 0, and the column, which is 2. And that way we can push the new cell onto the queue if it's a valid cell. So we'll keep track of the new row and column. So new row equals row plus direction at 0. And the reason why we're adding this, so we're taking the old one, which was, where was it? Which was 0, 1. And then we're adding whatever the direction was. Because based on the way we set this up, right, if our direction, like let's say our direction is right, because we're moving from 0, 1 to 0, 2, then that means our direction must have been 0, 1. Right, because our row is staying the same. That means that's what 0 means, because we're adding it. And then we're adding 1 to the column. which moves it to the right. So we're taking, you know what I mean. 0, 1 plus 0, 1 gives us 0, 2. So that's how we get the new row and column. So we're just going to do the same thing for the column and then take direction at 1 instead. Okay, now we're going to check for our invalid inputs, right? So if our new row is less than 0, then it's off the grid. Or if our new row is greater than or equal to the length of the grid, then that's also off the grid. Or, yeah, greater than or equal to. And same thing for the column. So if new column is less than 0 or new column is greater than or equal to grid at 0 dot length. And then our last check is that our grid, if I can spell, at our new row and new column is not equal to 1. So this is checking if we have a fresh orange there or not. So if we do not have a fresh orange, then either it is already a rotten orange, which in that case we don't need to re-rot it, or it's an empty cell, which in that case there's nothing to rot there. So we only want to go here if it's equal to 1. Wait. Is that right? I hope I said that right. Yeah, that's right. Then, okay, we're just going to continue. So we're just going to ignore that. Then after that, we are going to, so once we've done our check, then we can rot the orange. So grid at new row at new column equals 2. So it'll become rotten. Then the number of fresh oranges goes down by 1, and we are going to add that new cell into the queue to explore all of its neighboring oranges in the next iteration. So we'll add that to the queue. New int, new row, new column. All right, so that is mostly it as far as that goes. Let me pull this down so I can actually see where this ends. So, okay, then we're just going to do the entire while loop for all of the oranges until there's nothing left to explore. And then we're just going to do a quick check. So if fresh is 0, then we'll return the number of minutes that passed. So that if fresh is 0, we don't have any fresh oranges left, which means we successfully rotted all of the oranges. So then in that case, we're going to return the number of minutes that it took to rot all of the oranges. Otherwise, we are going to return -1. And I think that should be it. So let's test this out. Oh, okay. I think I just had a typo. Okay, let's try this again. Okay, there we go. Sorry guys, my brain is just like fried today, but I'm trying here. Alright, so our time complexity. I hope this isn't too hard to follow along and that my explanation actually made some sort of sense. So let's go through this real quick. So if we think about this conceptually, we are exploring the entire grid, right? Worst case. Because like worst case, let's say we have a grid that looks something like, and we don't care about the number of minutes because this is just an example. Well, actually, I don't even think it matters what's in the grid. Like, no matter what, we're kind of exploring the grid, right? Because, like, just to process it, we already have to go through every single row and every single column. So, already right off the bat here, we are going through the entire grid, no matter what. And so, yeah, this is already O of m times n, m times n, where I guess m is the rows and n is the columns, or whatever. And then our BFS is also O of M times N, because we are looping through, like we're checking each of the nodes or oranges or whatever's neighbors through the entire grid. So M times N, where M is number of rows in grid, columns in grid. Okay. Space is, so our data structure here is our queue, and we have this array for directions, but this is just constant. I mean, you can count it as constant because it only stores like 4 actual things in it. And it doesn't matter what our input is, like this is not affected. So it's really just the queue. And then in our queue, the worst case, it could store every single cell. So that is also just going to be O of M times N. With the same thing here. So yeah, that is it for this problem. Thank you guys for watching, and I'll see you guys next time. Bye!